So while we're here, I figured we'd do a little recap of polar versus nonpolar covalent bonds and then hydrogen bonds too, because why not? So if we are looking at a molecule, what we could do is we could figure out the electronegativity of the atoms. We could just look this up on the periodic table and see if there is like a medium difference in the electronegativity of those atoms. So if I do that for oxygen and hydrogen, I do find that. If I looked up carbon and hydrogen, their electronegativities are very, very similar, very, very close. And so they do a very good job of sharing electrons. So we would say they are nonpolar. This would be a nonpolar covalent bond. But here, between oxygen and hydrogen, there's enough of a difference, about a medium difference, between their electronegativity. And so when they go to share electrons, they're not going to do it very well. Oxygen is kind of going to hog them a little bit. So when that happens, we see poles. And by poles, I kind of just mean ends of a molecule where we have partial charges. And I'm going to use green to kind of just indicate what the charges are going to be. So we use the symbol, which is the lowercase d in Greek. It's a lowercase delta, to mean partial. Not like a full charge, but like a partial charge. So on this side of our molecule, the oxygen side, we're going to have a slightly negative charge. And it's going to be opposite that on the opposite side. So a partially positive charge on the other side. Kind of like a north and a south pole in a way. So we've got two ends of our molecule, negative on one side, positive on the other. And that happens because oxygen is a little bit more electronegative and is going to hog those electrons. Not going to be as good at sharing them as like carbon would have been. And so the electrons are going to spend a little bit more time hanging around the nucleus of this oxygen in that atom's electron cloud. They are going to go to hydrogen, you know. They're being shared. They're just not being shared that well. So we're going to see this pole happen. And so we say that the covalent bond here is polar. The electrons are not being shared equally. And we have another example, obvious example on the page. So let's just do that one while we're at it. So fluorine is our most electronegative element on the periodic table. So when it goes to share electrons with hydrogen, it is similarly not going to be very good at it. It is going to have a greater pull for those electrons, being more electronegative. And so this side of the molecule is going to be partially negative. I kind of think electronegative, more electronegative means partially negative on that side of the molecule. So this covalent bond holding them together is a pair of shared electrons, but it's not a very good sharing relationship. They're not going to be shared equally. They're going to spend more time around the fluorine because it's more electronegative. And we would just look up those values on the periodic table and see that there's about a medium difference between these two. And so that's how we know it would be a polar covalent bond. All right, so while we're here, whenever you have polar molecules near each other, and there's a hydrogen involved, then we start to get hydrogen bonding. So I'm going to toss in my partial charges on this water molecule over here, and then we're going to show a hydrogen bond happening between them. All right, and I'm going to use yellow for that. Actually, maybe not yellow. Let's use orange. Be a little easier to see on the screen. Okay, so here I've got a hydrogen on the positive end of one polar water molecule, and it's going to be attracted to the negative end of a different polar molecule. Happens to be another water molecule, but it doesn't matter. It could be anything. It could be attracted to, like this one, for example. All right, so when that happens, we're going to get this weak attraction. Now I'm going to draw this with like a dashed line to show that it's not as strong as a covalent bond, and so we don't want a solid line, so we're just going to use a dashed line and like a dotted line, and that's going to show this bond that is going to be happening between these two atoms on different molecules. So that's what's interesting about hydrogen bonds. They're not inside a molecule or inside a group of atoms. They're between two groups of atoms, between two molecules. And since they're weaker, they can break and form really easily, like as these water molecules are spinning and sliding around, being liquid, they'll break and form. If we cooled down our water and hit the freezing point, what would happen is we would form more of these connections while we're in that phase change. And we would see all of our water molecules start to form the maximum number of these hydrogen bond connections as possible. If we were melting in a phase change, what we would be doing is breaking these hydrogen bonds. Same thing with if we were vaporizing the water, we would be breaking all the remaining hydrogen bonds in order to really separate all our water molecules apart so they could then bounce freely around as a gas. Okay, so hydrogen bonds, weak connections between two polar molecules, between a positive hydrogen on one polar molecule and the negative end of another polar molecule.